general relativity that builds on these previous 4 episodes. If you haven't seen them, then pause me now, go watch them in order, and meet me back here after the music to hear about curved spacetime. Newton's and Einstein's dispute over gravity comes down to competing notions of what constitutes an inertial frame of reference. Newton says that a frame on Earth's surface is inertial, and relative to that frame, a freely falling apple accelerates down because it's pulled by a gravitational force. But Einstein says, nuh-uh, it's the apple's frame that behaves like a frame in deep space, so the apple's frame is inertial, and the Earth frame is actually accelerating upward. You just get a false impression of a gravitational force downward for the same reason that a train car accelerating forward gives you a false impression that there's a backward force. So who's right? Well, between our gravity illusion episode and your comments, we've seen that Einstein's position seems internally inconsistent. Remember that inertial frame in deep space? Well, the apple accelerates relative to it. So if inertial frames define the standard of non-acceleration, how can both of those frames be inertial? Today, we're finally going to show how curved spacetime makes Einstein's model of the world just as self-consistent as Newton's. Step 1 is to express both Newton's and Einstein's viewpoints in geometric spacetime terms, since that's the only way to compare them in a reliably objective way. Remember, humans experience the world and talk about the world dynamically as things moving through space over time. But even in a world without gravity, we already know that clocks, rulers, and our eyes can all mislead us. So to be sure we're talking about real things, as opposed to just artifacts of our perspective, we have to translate dynamical statements into tenseless statements about static geometric objects in 4D spacetime. Let's start with Newton. He says that spacetime is flat. Just think about it. On the flat spacetime diagrams of inertial observers, the world lines of other inertial observers are straight, indicating constant spatial velocity. This captures Newton's idea that inertial observers shouldn't accelerate relative to other inertial observers. Newtonian gravity would just be an additional force we introduce, like any other force, that would cause some world lines to become curved, i.e. spatially accelerated. This is a bit oversimplified, but for today, it'll do. Now for Einstein's position. This is actually more subtle, and it'll be easier to explain if I first set up an analogy using our old friend, the two-dimensional ant on the surface of the sphere. A tiny patch at the equator looks like a plane, and within that patch, 2 great circles both look straight. But suppose the ant believes that he lives on an actual plane and decides to draw an XY grid on a large patch of the sphere, with its x-axis along the equator and the y-axis along a longitude line. Relative to this grid, the second great circle looks bent, so the ant concludes that it's not a geodesic. But you see the ant's mistake, right? His grid is distorted. You can't put a big rectangular grid on a sphere without bunching it up. Try it with some graph paper and a basketball. It doesn't work. Stated another way, a sphere can accommodate local Euclidean grids in tiny patches, but not global ones. So the ant can use his axes as rulers and protractors within a patch, but not between patches. Flat space definitions of straightness apply over small areas, but not big ones. Okay, Einstein's position is that Newton is making the same mistake as the ant. Inertial frames, that means axes plus clocks, are the space-time equivalent of the ant's XY grid. If space-time is curved, then those frames are only valid over tiny space-time patches. So when an observer in deep space says that the falling apple is accelerating, he's pushing his frames past the point of reliability, just like the ant did. In other words, global inertial frames don't exist in space-time. However, global inertial observers do. They're observers that have no forces on them. Their world lines will be geodesics, and their axes and clocks can serve as local inertial frames, provided that we think of them as being reset in each successive space-time patch. And by the way, pictures like this are not intended to make literal visual sense. On the contrary, they're designed to break your excessive reliance on your eyes, so that your brain becomes more free to accept what reality isn't. Remember, no one can really see or draw space-time. There is no spoon. Now, the world line of a falling apple turns out to be a geodesic. It has no forces on it, so there's no need to invent gravity. Okay, but what about 2 apples in a falling box, like at the end of our gravity illusion episode? Remember, they get closer as the box falls. Now, according to Newton, that happens because the apples fall radially instead of down. But according to Einstein, it happens because the apples are on initially parallel geodesics that, since space-time is curved, can and do cross just like on the sphere. In contrast, the world line of a point on Earth's surface is not a geodesic. It has a net force on it, and it's really accelerating. So does that mean that Earth's surface has to be expanding radially? Well, be careful. In order to compare distant parts of Earth, you'd need a single frame that extends across space-time patches. But that frame can't be inertial, so any conclusions you base on it have to be interpreted with a heavy grain of salt. Okay, so Einstein's gravity-free curved spacetime sounds like it's self-consistent. But then again, so does Newton's flat spacetime picture that has gravity injected as a kicker. So once again, which of them is right? The answer is whoever agrees better with experiments, and there's over a century of experiments to refer to. Now, we haven't fully fleshed out all of general relativity yet, but there's one experimental fact that I can use to show you that spacetime must be curved, just based on what we've seen in this series of episodes so far. It's a cool argument originally presented over 50 years ago by physicist Alfred Schild, and it goes like this. Fire a laser pulse from the ground floor of a building up to a photon detector on the roof. Now wait 5 seconds, and then do it again. On a flat spacetime diagram, the world lines of those photons should be parallel and congruent. Without making any assumptions about how gravity affects light, that would be true even if it turned out that gravity slowed photons down and bent their world lines, since both photons would be affected identically. Now, if spacetime is flat, then clocks on the ground and on the roof should run at the same rate. They're both stationary. Thus, the vertical lines at the ends of the photon world lines should also be parallel and congruent. But if you actually do this experiment, you find that photons arrive on the roof slightly more than 5 seconds apart. The excess time is less than a nanosecond, but any discrepancy means that clocks are running at different rates, in which case the opposite sides of this parallelogram aren't congruent. And that's geometrically impossible if spacetime is flat. Thus, the very existence of gravitational time dilation, regardless of its degree, requires that spacetime be curved, and that means game over for Newton. In fact, to the extent that we can speak about space and time separately at all, most of the everyday effects on Earth that Newton would attribute to gravity are due to curvature in time. The 3D space around Earth is almost exactly Euclidean. Those pictures that you see of Earth deforming a grid the way a bowling ball deforms a rubber sheet, or even the pictures we sometimes use on this show, they all suggest spatial curvature only, so they're somewhat misleading. Remember, a frame consists of axes and clocks, and around Earth, spacetime curvature manifests itself in clocks much more than in rulers. So even though it's hard to visualize, it's curved time that makes the free-fall orbits of satellites look spatially circular in frames of reference that cover too big a spacetime patch. So why is spacetime curved in the first place? Unfortunately, the math gets heavier here and good analogies are harder to come by. But here's the flowchart level answer. Consider a region of spacetime. And remember, that means a collection of events, not just locations. Its curvature and geodesics are determined by how much energy is present at those events, via a set of rules called, no surprise, the Einstein equations. So for example, say you stick the energy distribution of the sun into the Einstein equations and turn a crank. What comes out is a map of the geodesics in the sun's spacetime neighborhood. Now when you translate those geodesics into 3D spatial and temporal terms, what you find is planetary orbits, or spatially straight, radially inward trajectories along which you would see spatial speed increase, or pretty much anything else that you would otherwise attribute to a gravitational force. It's pretty amazing. I want to conclude with a question once asked by one of our viewers, Evan Hughes. If there's no gravity, and gravity's not a force, then why do we keep using that word? Well, physicists are still human. As far as I know, most of us have no special ability to visualize or directly experience 4D spacetime. So we often think in Newtonian gravitational terms because it's easier and because the resulting errors are usually small. We just remind ourselves that it's just a crutch that we have to use with caution. But even when people are referring to relativity or string theory or whatever, it's just a lot easier to say the word gravity than to say curvature, four-dimensional spacetime.